let's just dive right into this explainer, shall we? We're going to uncover the hidden, honestly fascinating technology that perfectly orchestrates the absolute chaos inside an internal combustion engine. I mean, when you think about what makes a car go, you're probably picturing pistons pumping, spark plugs firing, and fuel burning in this massive, highly explosive dance, right? But there's actually a silent conductor behind all of this mechanical violence, and its sole job is keeping every single movement perfectly in time. So today, we're decoding the engine's hidden heartbeat, the Crankshaft Position Sensor. We're kicking off our investigation with a really relatable and, let's be honest, highly frustrating mystery. Why on earth can a single, seemingly insignificant component completely paralyze your vehicle, leaving you stranded in your own driveway? Look, we've all been there. You turn the key, the engine cranks and cranks, but absolutely nothing happens. Your battery is fine, the starter's working, there's plenty of gas in the tank, but the car just stubbornly refuses to run. How does one tiny piece of plastic and metal hold that much veto power over an entire machine? Well, the answer to that mystery lies in the Crankshaft Position Sensor, or the CKP for short. It's essentially a device that detects the rotational position and the speed of the engine's crankshaft. Then it takes that mechanical motion and converts it into electrical timing signals for the engine control unit, or ECU. Now here's what's really wild about this. The sensor doesn't actually control the engine directly. It doesn't fire the spark itself. Nope, it's just the ultimate messenger. It tells your engine's computer exactly where the crankshaft is and exactly how fast it's spinning. Without that constant stream of data, the ECU is basically flying blind, completely unable to handle critical stuff like fuel injection, ignition timing, and even misfire detection. To fully wrap our heads around this vital heartbeat monitor, we're going to look at a few things. First, the engine's rotational clock. Then, how the sensor actually works. Third, decoding the trigger wheel. Fourth, synchronizing the engine. And finally, number 5, what happens when things go wrong? Okay, let's start with section 1, the engine's rotational clock. The crucial thing to understand here is the environment itself. The crankshaft is this heavy, rotating shaft deep down inside the engine, and its job is to convert the up and down movement of the pistons into the rotational motion that actually turns your wheels. In a standard 4-stroke engine, a piston moves through 4 distinct phases, right? Intake, compression, power, and exhaust. Now, for every single complete cycle of those 4 strokes in one cylinder, the crankshaft spins exactly 720 degrees, literally 2 full rotations. The ECU needs to know exactly where the piston is within that 720-degree window. Why? Because the spark plug has to ignite the air-fuel mixture at a carefully chosen microsecond, usually just before the piston reaches top dead center on the compression stroke. If the ECU doesn't have an absolutely precise measurement of those 720 degrees, firing the spark or injecting fuel at the right time, yeah, that becomes completely impossible. Moving right along to section 2, how the sensor works. Let's zoom in on the hardware. Modern engines generally rely on one of 2 main technologies here. On one side, we have passive variable reluctance, or VR sensors. These little guys contain a permanent magnet and a coil of wire. As the metal teeth on the crankshaft pass by, they disrupt the magnetic field. This induces a voltage in the coil, creating a wavy, alternating AC waveform. It's totally passive, no outside power needed. But there's a catch. At really low speeds, that signal can be pretty weak. On the flip side, we have Hall effect sensors. Now these actually use an external power supply and contain internal circuitry to detect those magnetic field changes. So instead of a wavy AC line, the Hall effect sensor snaps its output sharply between high and low voltage states. That gives us a super crisp digital square wave. This provides a strong, crystal clear signal for the ECU even when the engine is just barely turning over while you're starting the car. Which brings us to section 3, decoding the trigger wheel, because the sensor is totally blind without something to look at. Check out this sequence. Tooth, 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 missing tooth, tooth. See, the sensor is usually mounted right next to a rotating trigger wheel. Sometimes mechanics call it a reluctor wheel. This wheel is covered in evenly spaced metal teeth. But think about it, if they were all completely identical, the ECU would just see an endless, meaningless stream of pulses. Sure, it would know the engine is spinning, and it could calculate the RPMs based on how fast those pulses are arriving, but it wouldn't have a clue exactly where the crankshaft actually is in its rotation. To solve this, engineers came up with the missing tooth pattern. A super common one is the 62 wheel. That just means it has 60 tooth positions, but 2 adjacent teeth are deliberately removed. That intentional interruption, it acts exactly like the 12 o'clock marker on a clock face. When the ECU sees that unusually long gap in the signal, Boom, it instantly establishes a known reference point. From there, it just counts the next teeth as they go by to know the exact crankshaft angle at any given millisecond. It's actually brilliant. Now for Section 4, synchronizing the engine. Let's pull back and see how this all connects. Remember how we said earlier that the crankshaft rotates 720 degrees, so 2 full times for one complete 4-stroke cycle? Well, that creates a bit of a puzzle. The crankshaft is in the exact same angular position during the compression stroke as it is during the exhaust stroke. So if the ECU is only looking at the crankshaft sensor, it knows the position for sure, but it doesn't know which stroke the cylinder is actually on. And this is exactly where the camshaft position sensor tags in. Because the camshaft only rotates once for every 2 crankshaft rotations, the camshaft sensor acts as the engine phase indicator. By comparing the high-resolution speed and position data from the crankshaft sensor with the phase data coming from the camshaft sensor, the ECU achieves this perfect, beautiful engine synchronization. This ultimate teamwork is exactly what allows modern engines to perform highly precise sequential fuel injection and dynamic variable valve timing. So putting it all together, the crucial path looks exactly like this 4-step sequence. Step 1, the mechanical crankshaft rotates, taking that trigger wheel along for the ride. Step 2, the sensor detects not changing target pattern, reading the teeth and, of course, that all-important missing tooth gap. Step 3, the electrical signal travels through the wiring straight to the ECU, which instantly calculates the exact engine speed and reference position. And finally, Step 4, the ECU acts on all this info, compares it with the camshaft data, and fires the ignition and fuel systems at the exact right millisecond. Oh, and here's a really cool bonus fact. The ECU actually analyzes the microscopic accelerations of the crankshaft between these firings to detect if a cylinder misfires. All of this intense math happens continuously, thousands of times a minute, just seamlessly working behind the scenes to keep your engine running smoothly. All right, let's wrap things up with Section 5, when things go wrong. Because, well, eventually they do. And this brings us right back to our opening mystery, summarized perfectly by this frustrating scenario. The engine cranks normally, but does not start. When the ECU completely loses that vital timing signal from the crankshaft position sensor, it is suddenly, terrifyingly, flying blind. Without a reliable signal, the computer literally does not know that the engine's internal parts are moving. So, as a protective measure, and basically because it simply doesn't know when to fire, the ECU will often just disable fuel injection and ignition completely. You turn the key, the starter motor mechanically turns the engine all day long, but combustion is absolutely never going to happen. But it's not always just a complete no start. These sensors can totally fail intermittently, and the symptoms we're looking at here are massive red flags that your engine's clock is losing time. For instance, an aging sensor might work perfectly fine when the engine is cold, but as things heat up, thermal expansion or internal resistance changes the sensor, and boom, it suddenly drops the signal. The result? You're cruising down the highway and the car just stalls unexpectedly. You pull over, let it cool down for a bit, and it mysteriously starts right back up like nothing happened. Super annoying, right? You might also experience hard starting, weird mysterious misfires, or you might look down and see our dashboard tachometer needle suddenly drop to 0, even while the car is literally in motion. And, for sure, that ever-present check engine light is definitely going to illuminate. Now, if you experience those symptoms, you might be tempted to just grab a basic multimeter and test the sensor. But a simple resistance test, it honestly isn't always enough. A sensor might show totally acceptable electrical resistance when the car is turned off, but still produce a weak, distorted, or intermittent signal once the engine is actually running and vibrating. And that is exactly why professional mechanics rely on an oscilloscope. By looking at the actual electrical waveform generated by the sensor in real time on a screen, they can visually catch missing pulses, incorrect amplitudes, or random electrical noise that a standard resistance test would completely miss. And this is a really vital point to remember. The sensor doesn't control the spark itself, it's merely the messenger. So if your diagnostic scanner throws a crankshaft position sensor trouble code, whatever you do, don't just blindly fire the parts cannon and replace the sensor. The culprit might actually be damaged wiring that's melting against the engine block, or maybe just a corroded loose connector. It could even be an incorrect air gap. Think about it. If the sensor is too far from the trigger wheel, the signal gets too weak, but if it's too close, the wheel might literally smash into it. You could even have a damaged trigger wheel with a bent tooth, or a stretched mechanical timing chain that has thrown the crankshaft and camshaft completely out of sync. That code just means the ECU is seeing a bad signal, not necessarily a bad sensor. So the next time your vehicle struggles to start, misfires, or just stalls unexpectedly on you, I want to leave you with this final thought. Is your check engine light actually pointing to a physically broken part inside your engine, or is your vehicle's brain just desperately searching for a lost signal from its hidden heartbeat?
As our engines become entirely digital, or even as they get replaced by EVs with completely different, complex sensor arrays, we really have to wonder, what new silent conductors are being invented right now to orchestrate the cars of tomorrow? Thanks for joining me on this explainer, and keep questioning exactly how the world around you actually works.